can you tell others to join? I'm giving 5 minutes. Please tell others to join who are there. So are you able to see my screen now? Am I audible and are you able to see my screen?
Yes.
Okay, thank you. So so what we can see that after expanding up to this one, we saw that the cost of this node was 5. The cost of this node uh, was 5 and cost of this node is 3, right? So in the next step we'll select this node to be the e node and we'll try expanding it. Okay, so now for this node, if you look at this, so the right move, so moving the empty slot towards right is not possible, right? Because it is at the verge of the right corner. So what will happen? So there will be only two moves available. Right is discarded. You cannot move to left as well because the previous move was right. Okay, so you cannot move the opposite direction. So left is not allowed. So only two move is allowed. One is up, another is down. Okay, so let us see. So if we move up, so 8 will come down. 8 will come down, and the empty slot will go up, right? And if we move towards right, I mean towards down, so 12 will go up and empty space will move down. Okay, so now if you try to find out the cost function of this, so now this node is how far from the root node? So there is 1 1 2 and 3. Okay, so yes, সৈকত is telling sir এখানটা কোন which place you want to be repeated? So what we are doing now, see, left toggle. Okay, so see, no, for this node. Okay, so for this node, what we have, see, you cannot this empty slot you cannot move to right because it is at the right border, right? So it cannot go right. Okay, now it cannot go left. Why? Because it has come to this node with a right move, right? It has come to this state with a right move, right? So if you go left, it will come back to this node again. So see, if you go left, 11 will in this place and empty slot in place of 11, right? Which is just as this one, right? So if you move so in this node, if you move in the opposite direction of the direction which leads you to this move, will make you loop through, right? I mean, so what will happen? See, if you go left to here, you will go in this way, and there again, when you will expanding this node, so it will again come back over here. So it will again, if you move left, it will go back there, and if you move right, it will go back there. So if you allow the opposite move direction, then it will be like flickering from between two states. Okay, so that's why we are not allowing the opposite direction move. Okay, the right direction here is for it has come to the right border, but the left direction it is not allowed because this was the right move. Okay, we come to this node from this node by a right move. Okay, so in this node we cannot allow the left move. Okay, opposite to this right move. Okay, so this right and this right is different. Okay, so that's why we there will be only two move. One is up, another is down. Okay, so if we move up, this will be the configuration. If we move down, this will be the configuration. Okay, Okay, so is it clear, Shoikat? Okay, thank you. So anyway, so if you see, so what will be the cost of this one? Okay, so for this node we will have cost like, so first of all, hx is the distance from the root. So distance from the root is 3, right? So here the distance from the root is 3, and how many of the tiles are the misplaced? So you can see that 8 is misplaced and 12 is misplaced, right? So two of them are misplaced. So the cost for this node will be 3 plus 2 5. Okay, so the cost for this node is 5. Now what is the cost of this node? So the cost of coming to this node from root is 3, and there is no misplaced tiles over here. Okay, you can see all of them are in same position, in its goal position, right? So the cost will be 3 plus 0, which is 3 itself. Okay, so now once we found that hx, uh, sorry, g cap x is 0 for some node, it means that node is an answer node. Okay, so it means we have come to an answer. This is an answer node. Okay, so that's why we'll stop further exploring the other nodes, and this will give us the answer node. So once we have got this node, what we have to do, we have to find out the path from the root to this node, down to this node, to get the steps. Supratim Pal, I think you are in. Please mute yourself, Supratim Pal. Okay. So now what we'll do? So you got the example, right? You got the idea how least cost branch and bound can be used to solve the 15 puzzle problem. Okay. So next, what we'll do is to try to implement this 15 puzzle problem, get to know about the algorithm. But the thing is, for doing that, we need the idea of priority queue. So what is a priority queue? So in case of least cost, we in so as we see in case of FIFO, we need queue. In case of LIFO, branch and bound, we need stack. In case of this least cost branch and bound, we'll need the priority queue or mean heap, whatever you can say. Okay, so priority queue is nothing, is basically mean heap actually. Okay, actually priority queue is implemented using mean heap, and there are few operations that is associated with this priority queue or mean heap. Okay, so what are they? So we need the operation. What are they doing? So extract mean heap. So extract mean heap, what it will do? So what is mean heap? So prior to going that, so you have done heap shot, right? For heap shot we are having max heap. So max heap is telling that the node, uh, any node is actually greater than, in case of max heap, any node is greater than all of its children, right? So in case of minif, what we will do? In case of minif, any node will be less than any of its children. Okay. So so in priority queue, we'll need this property. So in case of minif, we'll have uh, this is the least node. Then lower. This is will have lower value than two of its children. Okay. So what we'll do? Extract mean will. So now mean heap. In mean heap, the lowest possible value will be at the root node, right? As in case of max heap, you have done max heap in heap shot, right? So in max heap, the maximum possible value was in your heap root node, right? So in case of mini, the minimum possible value will be in the root node. Okay, so extract min heap, what it will do? It will takes out the root node of the heap. Okay, so let us draw an heap without any values, and let us suppose that this is a heap. So heap is a complete tree, right? Heap is a complete tree. So suppose this is our heap, and we are doing the extract min. So since this is a min heap, so extract min will take out the minimum value which is situated at the root of this heap. Okay, so we'll take it out, we'll extract it, and replace the root with the least with the last element of the heap. So this is the last element, right? So this is the last element. So we'll take this last element to the to the top as a root of the heap. Okay, and then we'll reduce the heap size by 1 because we have extracted the original minimum value, and we have taken up this value last node to the heap root, and we reduce the size by 1 as we have done in case of heap sort as well, and then we'll perform min heapify on the root. So next we'll apply, since we have taken a new node in the in the root node, so we'll apply min heapify in this. Okay, so min heapify, what it will do, it will compare its with its children, and whichever is minimum will take out into the root. Okay, and it will recursively call on the next node. Okay, so likewise upon calling this minify after in the extract min operation, what it will do, it will uh, it will make the heap again in a min heap after extracting the root. Okay, after taking out the root. Okay, so extract min operation, what it is doing, it is basically taking the root out or taking the minimum element out from the root, and again reheapify the other nodes. Okay, next is heap decrease key. So in case of priority queue, but this operation is directly not needed. Heap decrease key is basically used to decrease a key value. Suppose here currently I have value 9 for this node. Okay, now if we want that, okay, I want this node to be 7, because only decreasing is allowed, increasing is not allowed. So so we want to decrease the value at index to the key. So key is 7 and not by key. So we do not want this value to reduce by 7. We want it to be 7. Okay, so we'll not reduce by 7 and make it 2. We'll make it 7 only. Okay, so the decrease key operation does this thing. It will decrease the value at index to key. Okay, and check upward and swap is minif is property is violated. So what we are doing, so we are reducing the value of a node, right? So we are reducing value of a node, that is fine. That is fine for all of its children, because in case of min heap, this was the lower value from all of its children, right? But it was higher value from its parents, right? So once we do the decrease min heap, we have to check upward that whether it violates the mini property. Suppose initially this was 9 and this was 8, right? So this was holding the heap property, mini property, right? Now we reduce the key to 7. So now as soon as we reduce 9 to 7, heap property is violated, right? So that's why you need to check upward, and we need to if we mismatch is found, we need to swap. Okay, so we have to keep 7, take 7 upward and 8 downward over here. Okay, and if there are further parents, we have to keep on this checking until we found that there is a minimum value above it. Okay, so this is what the operation heap decrease do. It basically checks upward. So the difference between min heap is checking downward, because an heavier element is put over there, and that's why it is checking downward. And heap decrease key is making a node lighter, so that's why you have to check upward that whether it can go up or not. Okay, but the operation that will require here, heap decrease is not directly required. Here we'll require this min heap insert. Okay, so how will insert a node? So suppose this was our heap, that heap is now distorted. So how we'll do the insert? So suppose this is our heap. Okay, till now I am trying to insert another node in it. So we'll insert being a complete node at this position, right? So once we insert it, we have to increase the heap size by 1. Okay, and we have to add this heap position at the last position, and we'll perform heap decrease key on the increased heap size. Increased heap size means the last position. Okay, and the key value. So key value is itself only. So I am adding a key. So I have added that key, and I am trying to decrease it to that value. So it will remain that value, but this node will be added. Now once this heap decrease key is called on this index, so it will, what it will do, it will check for its parent whether this value is lower or not. So it will again check upward to up to root until a valid configuration is found. Okay, So mini insert will do this one. So it will add a new key and it will check upward. Okay. So it will check upward if the heap property is maintained. If it is not maintained, then it will swap. It will come up. It will if suppose for this node the heap property is not maintained after inserting, so it will come down and it will go up, and again it will check with the its parent node whether it is maintaining the heap property. If not, then it will again swap. So like this it will continue until heap property is maintained. Okay. So this is how the priority queue is implemented. So we will need these two operations, extract min and minif insert. Okay. So let's see with the help of this how will solve the 15 puzzle problem. So for 15 puzzle problem, so till that we have done the deterministic algorithm, right, where each step is told to you deterministically what you have to do. But here you will have a non-deterministic algorithm, because I do not found any deterministic algorithm for this 15 puzzle problem. They have only given only the examples. Okay. So I have written an on non-deterministic algorithm for you. You can use this algorithm, not an issue. So let us see. So non-deterministic algorithm is the steps are not fully defined. They will be, you can implement the steps in your way. Okay. So that's what it means. So start the root node and a priority queue based on the estimated cost of the states. Okay. So now here since we are doing LC means list cost branch and bound, we will have the uh, priority queue things. Okay. So now the priority queue is built upon some value, right? It compares the value. So what value will be compared? That is the estimated cost. The cost function, the value that is given by the cost function will be used to as the priority value of this priority queue. Okay. So we'll start with the root node and then priority queue and a priority queue based on the estimated cost of the states. Okay. And we'll insert the root node into the priority queue, and until the queue is empty we'll do the same thing. So the structure is similar. Okay. So we'll do the extract min to get the e node. So now see, we have done a priority queue, right? We have done a we are maintaining a priority queue of the states. So this priority queue at the root node will uh, have the node, have the state which is associated with the minimum cost, because we are maintaining the priority queue based on the estimated cost, right? So this root node will now maintain the minimum cost. Okay. So we'll extract min to get the e node, means we will get the state which are having the minimum cost value. Okay. That's why we require a priority queue in this scenario. So now what we'll do, check for all the valid moves for this node. So once we get the e node out of the heap, and we'll try to generate all the valid moves for this node. Okay. So the valid moves are left, right, up and down. Okay. Now if the node generated by move is an answer node, we'll get out of the loop. Okay. And okay, so another step is missing. So if the move is an answer node, we'll get out of the loop. And if the move is if the node generated by the move is not an answer node, so I'll add this over here. Okay. So if the node generated that is not an answer node, so we'll see that whether it is bounded by the bounding function or not. Okay. So if it is not bounded, then it will insert will use the heap insert. Okay. Heap insert operation to insert the newly created node into the heap. Okay. So once we put the new node into the heap, it will reheapify itself to make a min heap. Okay. So next time it will get to extract min, get to the loop and try to find out the extract min, and trying to do the extract min operation, it will always get the minimum cost value node. Okay. Minimum, it will get the node having the minimum cost value. So so that step is missing here. I will add that up. Okay. So once this is done, so what we will do, we'll then print the path from root to this node. Okay. So that is how we'll solve the 15 puzzle problem. Actually you can use this algorithm for any LC bound LC branch and bound problem. Okay. Or LC branch and bound solution. So there are two things. So first one is the number file video. So you can check this out. This video actually tells you that if an initial 15 puzzle configuration is solvable or not. So that part we are not doing here. So you can see it out, and you can also write the code over here. And next is the puzzle game. So puzzle game is the link that I have already shown, the link for this one. Okay, so you can possibly use this as a potential test case generator. So whenever you are writing this code, writing code for this problem, what you have to do, you have to have some test cases, right? So you click on this shuffle, it will give you some initial state, okay, and then you can solve it. I mean, then you can use this state, put this state in your program, and run it to see whether it can solve this or not. Okay, so this is theoretical part for today. If you have any question, you ask me, and next we'll move into the lab session where we'll do the same 15 puzzle problem. Okay. If you have any question, you can ask now. So we'll look into the branch and bound or 15 puzzle problem. The lab session will be a bit different. So for this problem, I will not give you any file where the instruction is written to you what you have to do, because this problem, solving this problem a bit longer. I have done it yesterday. So you can see the code has gone up to 335 lines. There are many comments as well, but it is around 300 lines of code. Okay, so I will leave it up to you how we will implement it, but I'll show you my code how I have done it and why I have done it. Okay, so you can get an idea, and then you can implement it, your code, and share it to me. So again, I will create an file for each all of you where you will have this thing. So let's see what we have done, what I have done actually. So this I have okay, so I have defined a type of position, okay, which will take the x and y value. Okay, so it will be required to for both. One is for your position of the hole, denoting the position of the hole, as well as your denoting the move. Okay, so suppose I want to move towards right, right? So if I want to move towards right, so my x position will be moved by 0 and y position will be moved by 1, right? So so for that move, we can also use this position structure. Okay, so the moves in this example I have done with this position example. Next is the state. So this state actually defines the state of that state space tree, and I have kept here a lot of information so that my computation is reduced. Okay, so let us see what are the information. So first is the board, 4 cross 4 board will be there. So I will have to maintain a separate board, okay, for each of the state. Otherwise we cannot work with the same board. সৈকত স্যার একবার বলবেন যে প্লিজ j cross 0. Can you unmute and ask? I am not getting your question. j cross 0 or y 1 হলো কি করে? আচ্ছা আচ্ছা, okay okay. So how x got 0 and y cross 1? Okay, I got your question now. See, I want to move to right, right? So if I want to move to right, how the coordinate, how the row and column will be changed. So if I move right, my row will not be changed, right? So my x axis will not be my x value will not be changed. Okay, So X is here used for row and Y is here used for column. Okay. You can also implement, so that is my implementation. You can implement as your, so X is denoting the row and Y is denoting the column. So if I want to move it to the right, I am here doing x0 and y1. Okay. If I want to move it to the left, I am denoting it x as 0 and y as -1. Okay, so here actually my in my example, the way I have implemented is x for 0, I mean x for rows. Okay, not for columns, and y for rows. Okay. Don't get it mix it up with the axis. Okay. So if I want to move up, so we'll have 0 -1, and if I want to move down, we'll have 0 +1. So this is how I have done with the position for moving the whole. Okay. So okay, so you can see. I'll come to that. So the next thing is I have defined the type state. State is having okay. Thanks, Aykot. So state is having so, so many information. I have keeping it with for each state, so that it is easy for computation. Okay, so you know the state space trade-off, right? No, state space, I mean, sorry, space and time, space time trade-off, right? So I have used a lot of space for this state, so that my execution time is reduced. Okay. So what I have taken in the state, one is board. Okay. So for each of the state, I will maintain a separate board. Okay. Otherwise, we cannot do it with a single board. Okay. So for each of the state, I will maintain a separate board, and for each of the state, I need to find out the cost, right? So how the cost is defined? Cost is the number of level from root, right? So number of level from root plus number of misplaced item. Okay, so these two information along with cost will be there, because see, these states are also will form the priority queue, right? Based on this cost value. Okay, so the priority queue will be based on this cost value. So I have to take this level value, I mean, how far this state from the root node, and in that node how many tiles are misplaced. Both this information will be there, and summing up these two will give me the cost of that state. Okay. And next will I have to put I have taken this value, the information about whole. Again, x means your the row value, and y means the column value. Okay. So the position have as I defined here, position have x and y, right? The position have x and y. So in this whole, x means the row value and y means the column value. Okay. So that is the position, and that is for move. So for each state where the whole is situated is given by this variable, and which move has make me to come this state will be there. Okay, so I have to keep the move in this state, because whenever I am generating a its children, I have to check that the children does not allow children is not allowed the opposite move, right? So for checking that it is not having the opposite move, I have to save this move, which move has bring me to this state. Okay, so that's why this move variable is there. So this move variable will hold uh, which move has led us to this state. Okay, whether it is right move or left move. So this is denoted by this position. Okay, and along with that we'll need this parent and next information. So parent information will be required from which whenever we are generating a child, a live node from the expanding node, we'll make the expanding node as parent of the live node. Okay, and we'll left the next node until we found an answer. Okay, so once we found an answer node, we'll go back to the parent and assigning the next node, so that I can come back from parent to the root node to the answer node. Okay, so see, whenever I am building the heap, I have only the upward pointer. Okay, there is no downward pointer. Okay, but to print out the solution, I need a downward pointer. Okay, so next is basically the downward pointer. So next will be having the pointer from root node to the answer state. Okay. and finally I am having the heap. So heap is heap of state pointers. Okay, state is this state structure that we have just created. So of that I have taken the heap size, maximum size of 1,30,000. In my machine, most greater than 1,30,000 is not allowed for making this element. Okay, so you can see that this is also sometimes incapable of solving all the problems, because the growth is exponential. The state space tree that is growing is exponential, and I'll show you when I have run some program on it. Okay, so I am creating a heap of this and having the heap property as this one. Okay, heap size and the elements. Now here this get misplaced tile count, it will take the board and find out how many tiles of it are misplaced. Okay, so while we are trying to find out how many tiles are misplaced, we do not count the position of the empty node, right? We do not count the position of the empty slot. Okay, so that you have to keep in mind. So this get misplaced tile count will give me the count of the misplaced tile of that state. Okay, get whole position, it will basically I will give the board configuration to here, have assign this value, and it will give me the position of the hole in terms of the x and y. Okay, so we'll take the input from user as a matrix, and from that we have to find out where the hole is situated, where the empty slot is situated. Okay, so this function get hole position gives us the empty slot. Okay, so next is get initial state. Now once we what we are doing, we are taking the 2D array, taking the initial state from the user, right? And once we get that board, that information in a board, right, the 2D array, so we will create the state from that board. Okay, so that board will be our first initial state. So this is our first initial state from the board that has been given by the user. Okay, so here what we are doing, we are basically assigning the board to board. So initially it will be level 0, right? This is our initial speed. So we are so how many of misplaced, so misplaced is we will get using this function get misplaced tile count of that board. Okay, so that will be assigned. Cost is so for the initial state, the cost state will be misplaced itself, right? Because the level is 0. Originally cost is the level plus misplaced, right? But cost, since level is 0, misplaced will be the cost for this initial state. Okay, now move x and move y. So for the initial state we do not have any move, right? So that's why it is 0 and 0. The initial states we are not having it from some move, right? So that's why it is both of them are 0. Now the position of the hole is given by hole, so that is given by the hole position that I have just shown over here. Okay, and next is initial. So this is the initial state, so it doesn't have any parent, and initially next is null for all. So that is how we are getting the initial state. So this initial state will give you it will take the board from the user and create the state type out of that board. Okay, and now see I have taken the 4 possible moves as a global variable. Okay, so in this move we are also initialize possible moves. So what are the possible moves? The possible moves are right moves, right? So in case of right move, I have x equals to 0 and y equals to 1. Okay, and then the left move. So for left move, I have x equals to 0, y equals to -1. Then down move, for down move we have x equals to +1 and y equals to 0, and for the up move we have x equals to -1 and y is equals to 0. So you can implement it as per your choice. So I have implemented it using the position type as 0 or 1. Okay, so that we can easily calculate something. I'll show you. So so first what we'll do, we'll get the board from the user, and from that board we'll call this get initial state. Okay, so the board will be converted to a state of that state space diagram, state space tree. Okay, and next we'll initialize the possible moves. Okay, so it will initialize, it will populate whatever the possible moves for all the nodes. Okay. So next we'll look through this move array, and we'll try to generate the nodes from these states. Next, I have done get a copy, so it will do nothing. It will dynamically create an 2D array of 4 cross 4 size. Okay, so a 2D array of 4 cross 4 size is created here, and the board which is being passed will be copied into the new array, and that will be returned. Okay, so this function will copy a board and give a new board that has have the same value as the old board. Okay, so old board will be there, a new copy of that old board will be created. This will be required for whenever we are generating a new state, we have to change the board configuration, right? So that's why from the current board I am creating a copy of the, as a new board, and in that new board I am changing for the current state. Okay, so that's why this copy of get a copy of the board is required. Next is inversion count of the board. Inversion count means uh, okay, inversion count. Actually, this function I was trying to implement whether to figure out uh, whether it is a whether the initial configuration that is given by the user is solvable by not. So for that, this get inversion count is required. But for you can skip this part as of now. Okay. So get inversion count will require in this part. So I am not explaining get inversion count. Uh, net is next function is get status of whole. uh, get status of all. This is also required for checking whether the initial configuration is solvable from the node or not. Okay, and again this solvable actually also checks that whether this initial state is solvable by the 15 puzzle algorithm or not. So these two, get inversion count and get status of hold, are used for this whether it is checking whether it is solvable or not. So we'll skip this part. Okay, next function that we have done is exchange, that is basically for exchanging two elements I and j, swapping the elements of an array. Okay, so we'll be given the array, will be given to position to index, and you have to swap between those two index. Okay, and that will be required in your min hippify. Okay, so this is your min hippify algorithm, same as the max hippify algorithm, only some conditions have changed. Okay, now the thing is, when we are doing the hippify, we have to do it on the cost, right? Whenever we have done for sorting the algorithm, sorting an array of integers, we directly have those values, right? We directly have those integers in the array, but here we'll have the state in the array. Okay, so array of states will be there. So what we have to do, we have to find out the cost of those states, and trying to build the min heap out of this cost. Okay, so this is the array, and this represents a state, and from that state we are taking the cost to compare the values. Okay, and this will give you, I mean, with this comparison of cost, you can build a min heap or build a priority queue out of this uh, cost, which is having the minimum cost will be top on top of it. Okay, and next is your heap extract min. Okay, so heap extract min will extract the top element, reduce the heap size. So it is taking the top element, that is element 0, and it is replacing the element 0 with the last element. Okay, heap size minus 1 is your last element, so it is replacing the 0th element with the last element. It will reducing the heap size by 1, and then it is calling the min heap by. Okay, so extract min will take out this 0th element that is at the top, will min, and finally it will return the min. Okay, so it will now extract the min. So I am not calling this heap decrease key from my algorithm. I have implemented this part which is actually in heap decrease key. Okay, in here. Okay, and sorry, no, heap decrease is used in min heap insert. So in min heap insert, what we are doing, we are having this heap, and a state has to be inserted in that heap. Okay, so we have to increase the heap size, and we have to put the state at the last position. Okay, heap size minus 1, last position. So once we have put that, we have to do the upward checking. Okay, so here we are doing the upward checking. We are checking with the parent whether it is maintaining the heap property or not. If it is not, we are exchanging the value and again checking upward that whether it is maintaining the heap property or not. Okay, so likewise the it is done. uh, Initialize queue. Okay, so initialize queue was also called from the main function. It is basically the priority queue, probably not the main function, not the solve function. So it will basically initialize the queue that will require for our algorithm to implement. Okay, so the queue is actually maintained. So this queue is actually priority queue. So priority queue is maintained by the heap. So heap is created and the heap is initialized with the current problem state. Okay, and then we return the heap as the queue. Okay, so next is valid move. Is valid move is checking that whether a move I am considering is a valid move for the current node or not. So what are the condition? One is opposite indicator, means whether the move I am doing is opposite of the move that I have done previously or not. Okay, so see how I have checking it. There are a lot of way you can check it. You can check the x and y value one by one. So if you can remember, in the state data structure, we have this move value, right, which holds the move which brings us to this state, right. So this move has again x and y value. Now this position move is basically the move that we are making for the child node. Okay, so we are checking that for this node, can a child node have this move or not. Okay, so now see how the value of how a value of move is. So it will be 0 comma plus minus 1. Okay, so if we move it horizontally, means if we move it only to the column left or right, we'll have either plus 1 or minus 1 in the y value and x will be 0. Otherwise we'll have plus minus 1 and 0. Okay, if you move it vertically upward and downward, right. Now see for a move, if the node move for the node was x, I mean this x. So if we multiply this to x value and multiply this to y value, what will happen? See suppose the move that was made by the node was 0 comma 1. Okay, it means we have the node was generated by moving the empty spot towards right. So what move is not allowed? The move for its children is not allowed is 0 comma minus 1, right. So this move is not allowed for so if your node has this move, this will not be allowed for your children, right. So how I am determining this? So I am multiplying x with x. So 0 is 0 and 1 with minus 1. So and summing them up. Okay, so I am multiplying the x's of that node and the move itself, and y of the node and move itself. Okay, and multiplying them and summing them up. Okay, so see one of them will have to be 0 and another will be minus 1, right. So opposite indicator will have the value minus 1 only when the move is opposite. Okay, otherwise it will have either 0 value or 1 value. Okay, so this function helps me save time for checking a whole lot of condition. Okay, for the up and down, left and right, all the conditions can be checked using this function. So this function will generate some value which will indicate that whether the move is opposite or not. Okay, this is one thing. So opposite move is not allowed. Another thing is so opposite, if opposite indicator has value minus 1, then only it is indicating an opposite value. If it is 0 or if it is plus 1, then it will not it is not an opposite move and we can allow this move. Okay, so opposite move greater than equals to 0 is an allowed move. Okay, next what we are doing, next we are checking for the whole, if we allow the move, so where it is taking us. So so we have x value of move and y value of move, right? And in node I have the position of hole in hole dot x and hole dot y. So I am adding up hole dot x plus move dot x to find out the new position of the hole. Okay, new x value of the hole. Similarly, new y value of the hole. Okay, and this new x and new y value has to be between 0 and 4, right? Otherwise it will go beyond the boundary, so that will not be allowed. Okay, so new x and new y value has to be between 0 to 4. Okay, that checking has been done. So if it is so for this node and move that has been passed to this function, if it is a if it is not an opposite move and the value of new value of x and new value of y of the whole belongs to the range of 0 and 4, then it is a valid move. Okay, then we can allow this move. Okay, so so the trickier part is here, how we have saved a lot of time by not checking using this function. Okay, anyways, next is updated misplaced count. Okay, so what we have, see, when we are trying to find out the cost, what we are doing, we are basically moving the whole up, down, left, right, and we are again recalculating the cost, right? Now, if you think deeply, that whenever we are moving a whole, the cost can be changed at most by one, because only one position is changed, right? So the scenario is when you move an hole, uh, so when you move an hole and original tile is moved to the old position of the hole, right? So an original tile moves and the hole gets shifted, right? So what will happen to the tile that has been moved? So it might happen that the tile which is moved to the correct location from incorrect location. So what will happen? So when you move the tile in the next move, when you move the tile to the hole, it might happen that the the tile was initially in correct position, and as you move the hole, the tile gets to its correct position. Okay, so at that time what you have to do, the misplaced count, whatever was the misplaced count, that misplaced count will be reduced by 1. Okay, so that's why I am checking that whether whether the new position, whether the value actually belongs to that new position. Okay, it means that if it so this function, again this function actually gives me, for the x value and for the y value, what should be the value in the goal state in that position. So that will be 4x plus y plus 1. Okay, so that is what I am doing. So with the position value x and y, 4x plus y plus 1 actually giving us the value that should reside at that location xy. Okay, so if the value that I am considering after the move, if the uh, value is same as this value, this function generated value, it means that it has now moved to a correct position. Okay, that's why it is returning -1. Means the misplaced count has to be reduced by -1. Okay, so update misplaced count by returns us how many by how many items we have to update the count. Okay, so we have to reduce the count by -1. Okay, next what will happen, next if you move the empty space, it also might happen that that the that the tile you have moved, it is moved to an incorrect location from the correct location. So it might also happen, suppose for an configuration that the hole is there, and prior to the hole are some value which should be there. I mean, okay, let me show an example. Suppose suppose for this example, okay, so here was the hole initially. Okay, now you can see that, so see 6 is in the correct position, right? So if you move 6 to the right position and hold to the left, so what will happen? 6 is from correct position, 6 is moves to some wrong position, right? In this example, right? So if you move 6 to the right, So it will come to the wrong position from a correct position, right? So what will happen if you do this move? The wrong count, the misplaced count will be increased by 1, right? So that is what has been checked by this condition. Okay, so see, this is actually for new position. So if in the new position, so for the first condition, if it is the in the new position, uh, where the value is moved is same as the value that should be in the new position, then it has moved to the correct position. Okay, now if the value in the if the old position generates this value, it means the value was correct in the old position, right? It is not correct in the new position. So it means it has moved from the incorrect location to the correct location. Sorry, moved to the incorrect location from the correct location, right? That's why the misplaced count has to be increased by 1. Okay, and finally move the incorrect location from incorrect location. If this is not the cases, then it might happen that uh, it has moved from some incorrect position to incorrect position. Here actually we do not have the example where they move us where they move leads us to the incorrect position to the incorrect position. But that may also be possible that a misplaced tile is okay. So I can probably find it over here. Yes, see, there is in this example 7 8, all of them are misplaced, right? Now if I move 8, so see, 8 was not in its place initially, and now if I move 8, 8 is also not in its place now. Okay, so in the old position it was not in the its original place. Again in the new position also it is not in the original place, right? So if it was originally in the wrong position, and it also in the new place in the wrong position, then the misplaced count will not be increased, right? Because it was already counted there. Okay, so misplaced count will not be increased. So by this function, what I have done, by this function uh, I have optimized the finding of the misplaced count. Okay, what you can do, you can once you have done a move, you can check thoroughly that what is the misplaced count, right? But by incorporating this function, I am just checking how much count has been updated. Okay, so whether it is 1 or -1 or 0 for a move, and I will add up this value with the existing misplaced value. So that will give me the new misplaced value. Okay, and then you would have the make move operation. So here actually what we are doing, we are making the move. So we'll have given a node, expanding node e node, and we will be giving the move. Okay, and with that expanding node information and move information, what we will do, we'll create a live node. Okay, we'll create a live node and we'll assign the value of the state. So how we are doing that, we are using a copy of the board of the e node or parent node. Okay, and we are next finding the new hole position. So in this live node, where will be the hole position? So hole position will be uh, parent's hole position plus moves x value, right, plus parent hole positions y plus moves y value, right? So this will give you the hole position in the new live node. Okay, and next what you have to do, next you have to find out that next you have to move the tile. Okay, so this is see how I am moving the tile. So I am taking the old hold position, right? So now in the old hold position will in the new board the old hold position will replaced by a tile, right? And which tile it will be replaced? It will be replaced by the tile which was in current hold position, new hold position, right? So so that's what we are doing. So we are moving this line, actually moving the tile and shifting the hole. Okay, so once we have moved the tile, we are assigning the 0 to the hole position. So in our example 0 is assigning the hole. Okay, uh, so live node will move, so we'll save the move for this live node as well. And now we are counting the misplaced count. So how we are counting the misplaced count? So we are not iterating through the whole board to finding out the misplaced count. What we are doing, we already have some misplaced count in the parent node, and we are now we have now called the update misplaced count. By this will basically see, this will give you the delta value, okay, how much value has been changed in the misplaced value, and add them up with the parents value to get the new misplaced value, okay. So this will save us from a lot of iteration. Now live nodes level, I mean the level for the child node will be parent node level plus 1, okay, and the cost will be uh, live nodes level plus live nodes misplaced, okay, and parent will be the e node. So that's how we are populating the new state that has been generated from the e node, okay, and the e node and the move. And once the state is generated, we are returning the state, okay. Now with all this function, we are basically having the solve function, okay. So in solve function, what we are doing, we are creating the queue, and we are initializing the queue with the initial state, okay, initial problem state, and then we'll iterate until the priority queue is empty. And what we are doing, we are checking, we are doing the extract min operation, okay, out of this queue. So extract min operation will give us the node having missed minimum cost, okay. And now what we will do, for this e node, there are four moves available, right? Up, right, left and left and right, up and down. So for those moves, what we are doing, we are taking one moves, okay. So one moves at a time and checking whether it is a valid move for this e node. So is valid move is telling us that whether it is not in opposite direction, and the values of the moves are values of the position of the holes are between 0 and 4, right? So it will take the e node currently which we have got from the heap extraction, and take the moves and try to find out whether this move is valid or not. So if this move is valid, okay, so we'll call the make move. So make move will create the new child node, okay, that is the new live node out of this e node and this move, okay. And now what we'll do, we'll check that whether in that new child node or the live node is the misplaced count is equals to 0. So if the misplaced count is equals to 0, it means that we have reached to an answer state and we'll break, okay. And if it is not 0, what we'll do, we'll do the heap insert key. So in that, so we'll now so since this move was valid, we'll now insert the new generated node into the queue, okay. So I have printed here the queue size, heap size, so that you can understand the heap is increasing, okay. You can also comment it out, but anyways, so that is what we are doing. This is basically our algorithm. If I come to the slide, so this is basically our algorithm. So we have created a priority queue, we have inserted the root node into the queue, okay. So we have inserted the root node into the queue, and next, while the queue is not empty, so queue is not empty is checking by the heap size greater than 0, okay. So while the queue is not empty, get the extract use extract min to get the e node. So we have done the extract min, okay, to get the e node, and then check for all the valid moves for this node. So for all the valid moves, there are four moves, right, which are in the which are in this moves array, okay. So we are iterating through these four moves and checking whether this moves is valid move for this e node, okay. So if this is a valid node, so if the node generated by move is an answer node, so how can we get the answer node? So answer node is given by misplaced count by 0, right? So if it is 0, then we are getting the answer node, we will break out of it. Otherwise, we will insert this newly generated node into the priority queue, okay. And then it will check for the next move, okay, whether the next move is valid, and again do the same thing. So in this here it will do the thing. And so once it get the misplaced count will 0, it will get out of that uh, for loop for the moves, and then it will again break for the while loop, okay, that is for the extract min, that is for this empty queue check, okay. It will get out of this loop because it has found the answer. Now what we are doing here, see, we are now basically creating the path. We have only downward pointer via parent, right? We do not have next pointer. We have assigned null to next pointers. So now we'll for the from this live node we'll get into the parent. Okay, we'll loop through this we'll to get into the parent, and while we are moving node by node towards parent, we are assigning the next pointer, okay, to this live node. So this way we'll have a downward path from parent to this current answer node. Okay, so now once we have the solution, we have to print the solution, right? So this is the your code for printing the board actually. And whenever we have 0, 0 implies the empty spot, so whenever we have 0, we are placing a space in that place. Okay, next is print state. So print state is I have used for checking whether my algorithm is correct or not. I mean, to get the intermediate values of that nodes. Okay, it is actually not required. You can use it, you can do it, you can use it to find out how the nodes are generated or how it is working, what the nodes are having correct, whether the nodes are having correct value or not. So I have actually written this code for debugging purpose actually. So again, print solution. So print solution will take the initial node, okay, and it will get to the answer node by following the next pointer. Okay, and it will print out the it will use the print board to find out I mean, for that node what is the board. Okay, and the main. So with all of this function we have done the original code of main. So here we have creating the 4 by 4 integer array. So you may ask why I have used that dynamic allocation. This is because I am passing this board to various function. Okay, so since it was giving me a warning like I am passing a local variable pointer to others, so that's why I'm creating a dynamic allocation. Okay, to avoid the warnings and any unprecedented error. So anyways, so next we are getting input from the user. Okay, so we will be expecting 0 in place of empty slot. Okay, and we have got the input over here. Once we got the input, we are initializing the possible moves, where we are initialize the moves array with the 4 value, right? Up, down, left and right. Okay, so this will be initialized. Then from this board that has been given by the user, we are calling the get initialize state, which is basically wrap up this board as a state of the state diagram. Okay, and then we are calling the solve initial solve function, which will basically use the branch and bound least cost branch and bound algorithm to solve the answer, to solve this puzzle. Okay, and once it solves the puzzle, we now use this print solution function that will basically print the solution from the root node to the answer node. So this is how it will work. Okay, so I will run this example. I will run this program and I'll show you few example how it is working. And next, so you got an idea. You have to write the code of your own. This time I will not giving you any instruction of how the code you have to done. Okay, you will do it from now on. Actually, not for this time. From now on, you will do this code of your own. Because see, what I am trying to do initially, if you can remember, I have given you those framework, right, where you are doing the automatic testing and all. So you at that place you have to write only the code of the algorithm, right? You do not have to think about the inputs and outputs and all. So in the next step, for some of the algorithms, till after the sorting algorithms, what we have done, there you have to write the code. You have to write the code following the instruction that I have given to you. Okay, so now you have to you have the instruction. What you have to do, and you are doing. Now what you will do, you will have to think by yourself that what you have to do, and you have to do it accordingly. So gradually I am trying to broaden your thinking. Okay, so initially you have to write only the algorithm, then you have to write as per my instruction, but code you have to write of your own, and now you have to write the whole thing of your own. Okay, you only know how to do it manually, and now you think how to implement it using computer. Okay, so from now on, those kind of instruction on the files will not be given to you. So let us run this. So let us enter some initial configuration. So this is the initial configuration for which we have drawn the state space tree. Okay. So okay, so let us look at this state space tree. So this was our state space tree, right? 1 2 3 4. Initial configuration was 1 2 3 4. Next 5 6 empty space, that is 0 8 9 10 7 and 11, and 13 14 15 and 12. Okay, so if we do it, so see what we are getting. uh, there is one thing. So the initial state also, it is there is mistake, so it has to be moved 0. Okay, so I'll update that. So what it is doing, see, so as per this state space diagram, how it is moved. So first it has to move down, right? uh, because it has the lowest cost 3. See this space, it was initial configuration, this space is now moved down, right? And next what we have, next as per this diagram, we have this the right move. Okay, so see, here also, from here we have a right move. So 11 has come up here and the empty space have gone to the right. And next from here we have a downward move. Okay, so 12 will come up. So from here there is a down move, so down move 12 will come up, and this is the solution. Okay, so see, this is one of solution. uh, so let us try to run few examples so that you can understand how this branch and bound or backtracking algorithm grows. Okay, let us take another example, uh, which one is like 5 1 7 3. Okay, next is 2 11 10 6. Next is 9 14 8 12, and next is 0 13 4 and 15. Okay, so let me copy it because we'll use it once more. Okay, so let me copy it, paste it here. So now if you press enter, you can see this moves are generated. Okay, so there are 25 moves actually which is generated. Okay, now you might wonder that how many nodes is created actually. So let us see the heap size for this example, and you will understand how many heaps are created actually. So I have the heap limit of 1,30,000. Okay, and let me just comment. Oh, I mean, let me just print the heap size in the solve. So here I am printing the heap size. Once I am inserting something into the heap, I am printing the heap size. Okay, so if I run the same example, now you'll see that the heap size increment of the heap size. Okay, so for this example it will take around 30,000 heap. So you can see there are 25 moves and 33,254 items were there in the heap. Okay, so you can understand how quickly this exponential function can grow. Even there are some problem which may not be solved because of we will be running out of the heaps. Okay, so let us see, so how we can test. So once you write, so you can take this kind of configuration. Okay, to to check your program. So that's, I have given the link in the PPT. So you can once you write your program, you can run this and you can generate is you can shuffle it to generate a problem state. Okay, so once the problem state is generated, what you can do, you can take input from this and see whether your program is working or not. So empty space means 0, then I have 10, then I have 3, then I have 11, next I have 8 and 7 and 13 and 1, next I have 9 and 5 and 15 and 4, next I have 2 and 14 and 6 and 12. Okay, so it might not be, so if the heap size reaches 1,30,000, the program will crash. Okay, and it will not able to solve this problem instance for using our program. So let us see whether this problem instance can be solved or by not. So it has reached to the top heap size, so that's why it has exited. Okay, so there are other instances like which can be solved using this heap size. So that's why I have printed the heap size to understand that whether the algorithm is not working or whether the heap size is going too much. So what I will do, I will also try to modify this to find out whether any duplicate heaps duplicate state is there or not. So that I have to check that checking was not there in the program. But anyways, I think you have got an idea what you have to do. This program actually will be a bit longer because of implementation. You have to implement the min heap priority queue, and then you have to use these, so many things are there, so many state checking and all things are there. Okay, so you will do it and so that's it for today. Okay, so if you have any queries, any questions, you can ask. Okay, then let's end it for today. We'll likewise we have done, so we'll do this session together. Okay, the theory and lab sessions. Okay.